Well, I got sunshine on my face. It's pouring in from a port light on my sailboat. Should pass in a moment. I can read the screen just about. Can you prove the 3x+1 problem by computation? And it's a bit of a strange question, and there are a lot of other questions I could have used, but I think about the Collatz function, the one the conjecture is based on, as just being a very, very simple algorithm. And I think it will be solved by computation. And actually, I think a good analogy is the four-color theorem, which was proved by computation. So I'm going to show you why I think it's really a very orderly algorithm, and that the output is much more predictable than it is assumed to be. But I'll just mention what the conjecture consists of. You have to prove two propositions, and I've turned them around and I made them prove two propositions are false. That's the way I'm stating it here. And one of those propositions is that there are sequences that diverge infinitely from one, and there are sequences that loop. And the first one is really, let me be clear, so they diverge infinitely from one, but they never go to one. They never touch one. So a regular sequence always ends in one. But they're looking for a sequence that starts somewhere in infinity and goes off to infinity. It never comes to Earth. So you could, in this little diagram on the top left, you can imagine it maybe doing a orbit around one, or a partial orbit, and then going off back into space. And the other one, the sequences that loop, this is pretty misleading as well, and I'll probably explain that right at the end, what a loop really is. That'll probably be my last slide, my bonus slide. Let's move on. So here are sequences from 3 to 47. Yeah, forget about the top row because the one is missing. So we can look at 27. That's a long one, and we're just showing the first few steps. And 27, 41, 31, 47, 71, and so on. And I've removed the even numbers, and that makes things a lot more concise. And you're wondering what these blue lines are on the left of the first column and the right of the second column. Well, they're two things. They are denoting that all the information you need about a sequence is its first step, following the odd consecutive integer. It's just the first step after that. That tells you everything you need to know. And let me just illustrate that with, if you go down to about sixth row, you see a 3. And then you go down another 4, you see a 5, and then another 4 rows, and you see a 7, and another 4 rows, you see a 9. So right away, you see that this is actually, this output is much more orderly than you would have suspected. And in fact, it's 3 interlaced series of numbers, which I'll show in the next slide, I think. And the reason it's so regular is because it's based on 3 operations that are determined by the congruence of the odd consecutive numbers. And there are 3 letters that I'm going to apply to those. And so every 4th number the letter repeats. Actually, the ratio is one letter that is twice as frequent as the other two. I'll try to explain that later on. The other thing that these lines denote is you can think of this as a Turing machine. So this would be the tape on a Turing machine. It's vertical in this case, it could be horizontal. Typically, I think it is. So this contains all the computational information you need. Strictly, you could reduce it to one column. But then the head, the thing that reads the numbers and instructs the tape what to do next, would need to know more about the functions. All it needs to know now is to read across. So we start with 23. So say the head is on 23. It then reads 35. Then it moves the tape up, so 35 is under the head. And then it sees 35 and it says, oh, got to move to 53. So unfortunately, that's off this tape already. So I started in a really bad place. Let's try. So 11 reads 11, sees it's got to go to 17. Tape goes up, 17. Sees it has to go to 13. Tape goes down. Sees it has to go from 13 to 3. Tape goes up. And then again it goes up from 3 to 5. So that's why it's a Turing machine. And it doesn't necessarily, it shows it's a finite, it also shows it's a finite state machine. And usually, if you know the states going into the system and the transitions and then the output states, you have a deterministic system and one that you can know with certainty what's going to happen to it. But maybe I'm getting ahead, but let me just say that with a Turing machine, there's another conjecture called the halting conjecture. And the halting conjecture says that you cannot know for sure, based on the inputs, whether any Turing machine is going to stop or halt. It will for some inputs, it won't for others, but just seeing the inputs doesn't tell you what will happen. But if the Collatz conjecture is true, the Turing machine will always halt on 1. It has to halt on 1. So that's the connection there. I just want to say one other thing. You're seeing a lot of 3s here, and in the conventional 3x plus 1 function you won't see any 3s. The only 3 you'll see is the very first input. So that's because I'm using a different function. I'm using a superset function. Whatever's true for the superset function is also true for the conventional function. So I pointed out this series of numbers which are interlaced, going interlaced in the columns. So there's one sequence which goes 3, 7, 11, 15. So the gaps are always 4. There's one sequence that goes 1, 9, 17, 25. The gaps are always 8. And there's one sequence that also goes every 8, starting with 5. And they are different in the sense that they have different congruences. And so I'm calling these A, B, and C. And really what these congruences are saying is, well, n is an odd number in all cases. So n plus 1 is evenly divisible by 4. N minus 1 is evenly divisible by 8. And then if neither of those are true, n minus 1 is evenly divisible by 4. So the difference between the A and C is that one is plus 1, one is minus 1. And that's an important difference. Moving. So here I've made an input-output table with those 3 letters representing congruences. And we can go down one of them and say 7 goes to, input 7 goes to output 11, input 11 goes to output 17, input 15 goes to output 23. So this is the operation that applies to A. And you can see actually it's approximately 1.5. And remember, we have to add 1 and subtract 1. And we'll look at that operation in a coming slide. B is input 9, output 7, input 17, output 13, input 25, output 19. And the third one, C, is actually pretty easy to see that it's -1 divided by 4. So so let's say 13 minus 1, 12, divided by 4, 3. 21 minus 1, divided by 5, divided by 4 equals 5. 29 minus 1, 28, divided by 4, 7. So C is easy to understand, and you'll notice also that all the odd counting numbers are in the output column, which is actually a very nice piece of evidence to show that all Collatz conjectures converge, because they all, there's always a convergence on one of these odd integers. There's always an odd integer for the sequence to converge on. Now I'm going to demonstrate the 3 operations A, B, and C. So these correspond with the congruences A, B, and C. And the first one is odd number plus 1 times 1.5 minus 1. And so that's approximately multiplying the number by 1.5. So this operation is making the number bigger. So operation A is equivalent to the Collatz function, where it's 3n plus 1 divided by 2 once. And so my version is for 11, it's 11 plus 1 times 1.5 minus 1. 17 is the answer. For the conventional sequence, it's 3 times 11 plus 1, 34 divided by 2, 17. So you see it has the intermediate even number, whereas mine just goes straight from one odd number to the next. Operation B is similar. It's just you have division by 2 twice. So for me, I'm actually using this operation of multiplying by 0.75. So it's a reducing operation. It makes the number smaller. So for 17 minus 1, 16, times 3/4, 12, plus 1, 13. And then for the conventional function, it's 3 times 17 plus 1. So I think that's, I'm not, oh, is that 52? Sure. Divided by 2, 52 divided by 2 twice is 13. Right. So always the same odd answer, or well, at least for operations A and B. It's a little bit different for C. In operation C, the conventional function divides by 2 at least 3 times, but it could be more. It could be any number, because you have these cases of powers of 2, like 64 is the powers of 2, in which case you're going to have, I don't know, maybe 8 divisions by 2. For me, in this case, 29 minus 1, 28, divided by 4. Does that seem right? Yes, it becomes 7, of course. It does not become 11, that's why I put it in parentheses. Whereas, for the conventional function, you, with the division by 2 3 times, you end up with 11, and you don't even have 7. 7 is hidden. And this is really important. I'm not sure if I'm going to be able to explain it properly in this presentation, because I want to make this fairly concise. But so this feature, m-1 divided by 4, is not possible. The result of that is never shown in a Collatz sequence. It's hidden by these even numbers. But now the interesting thing is that when I come out of this this intermediate odd number, which I call a superset number, the next one will be the correct number, and it's obeying the same rules. And in this case, it's operation A, which makes it 11. If it could be operation B. That's the thing with operation C. You can consider this a merge between two sequences. One is coming from a C operation, and the other one is coming from either an A or a B operation. I'm not sure if I'm going to be able to illustrate that. Here I've put together the complete function. This is my function. And this is the critical part of it, this m-1 divided by 4, the bit that people who look at odd, even, or even odd sequences never see. And it's absolutely key to understanding the way sequences behave and why they must end in 1. So I've just associated just to take the first one, A, so n plus 1 times 3 over 2, which is 1.5, minus 1. That's the operation to perform if n plus 1 is congruent 0 mod 4, meaning evenly divisible by 4. n plus 1 evenly divisible by 4. So that is the complete function. This is a miracle function. I came up with this a few years ago and never found anything like it, and it unlocks so many hidden boxes to do with the conjecture. So one of my insights is that factors of 2 for n-1 or n plus 1 are absolutely critical to determining whether a sequence is going to add or lose steps. And the huge cosmic joke is, in every case, you lose a step. So whenever an operation occurs, you never get an extra step. You're one fewer steps closer to 1. And this applies even to the operation that increases numbers, increases the magnitude of numbers. So if we look at A, operation A, and that's the only one that increases numbers and is multiplication by 1.5, what it actually does is remove a factor of 2 and replace it with a larger k or a factor of 3. In fact, I think that's a mistake. I should show another 3 there. That's what usually happens, and I can show you on the following slide. So one factor of 2 goes away, and every factor of 2 represents a step. And the way to understand that is to look at the even-odd sequences and the division by 2. So a factor of 2 in the odd-only sequences minus 1 is the same thing exactly. So this is really important, and it applies, very clearly to the second case, B, which is multiplication by 0.75. And of course, whenever you multiply by a fraction, even though it's a whole number, you're not going to get another 2. You're going to get another 2 if you double the number or half the number. In the third case, C, well, this is the contradiction, but it's true. The operation does not remove one or more factors of 2. What it does, it divides k by 4, because k is divisible by 4. We established that with the congruence. So yeah, so k, k is divided by 4. Now, I'm rushing ahead, but this is the inverse operation. This is the inverse function. This is the perfect inverse function of the unorthodox function I showed you 2 slides ago. And the critical difference is, well, the whole thing is somewhat different. The congruences are different, but the only thing you really need to understand is the third case, which is an otherwise case. It can occur in 2 situations rather than 1, and in other words, 2 congruences, and it's n times 4 plus 1. So it's multiplying by 4 and adding 1. Now this is a huge inverse operation. This is, you know, no sequence could fight this and go to 1. And in fact, you know, it exactly reverses the sequence to 1. This one really does go to infinity. Why does it go to infinity? Because it adds a step with every operation. With every operation, it adds a step. It's that simple. You know, if you don't believe me about this, consider every number in the number line can be multiplied by 4, add 1, and the sequence it produces is 1 step longer. Believe me. So just to take the most banal case, 5 to 1 is 1 step. Multiply by 4 and add 1, you have 21. Then you have 2 steps. Multiply by 4 and you have 85. And you have 4 steps. Did I say that? 4 steps. So this is a guaranteed repeating feature in the number line for sequences. You know exactly what's going to happen, how often a sequence is going to be repeated, just by multiplying by 4 and adding 1, and you can do this over and over again to infinity. It will always be true. So that's huge. This is a sequence beginning with 111, and I chose it because it fits. It's actually in the same sequence as 27. It's about halfway through, which means it's the same sequence. I don't think you'll see this in the even odd sequences, because 111 is divisible by 3, and you know how I know it's divisible by 3? You just add up the digits. So 1 plus 1 plus 1 equals 3. That's a trick. It works with in any case, as far as I know. So here I'm going to demonstrate what's happening with congruence A when it recurs sequentially. So in the enlargement, or the blow-up, I've got the odd numbers, obviously, on the left. The third column has the plus 1 or minus 1, but since it's all A, operation A, it's plus 1 in every case. And you'll see in the first row that you've got 6 2's, and in the second row you've got 5 2's, and in the third row you've got 4 2's, and so on. And what's taking the place of those 2's? 3's. Extra 3's in every case. So the numbers are increasing, yes, but the factors of 2 are decreasing, and as I just said, it's division by 2 that determines the steps. If you look at the even odd sequences, whenever you remove, whenever you divide by 2 one or more times, you get 1 fewer steps. Oh, I'm already at the end. So what I have shown is whatever operation acts on a number, in every case on a sequence, and it's always a mixture of A, B, and C in some proportion. I don't know if it's possible to prove C is present in every case. That would be an important point. I mean, it is, but whether you can prove it or not, is another question, because there's always this, it is it is in the odd only sequences, and in fact there's a convergence on every number which has one C and either A or B. Every integer in the number line has a convergence, or a potential convergence, which is one C and then either A or B. So if we believe what I'm saying, and I do, that all the operations are direct, forward operations, they're not inverse, they cannot be never can they be inverse. They are never inverse. You cannot add steps to a sequence. You have a fixed number of steps. It may be very, very long, but it is finite. You're starting with whatever n you choose, no matter how huge. The sequence is going to come to an end because the steps are going to run out. And there's nothing mystical about this. The problem is that people imagine infinity and they think there's a pre-existing sequence that could be infinite. No, there's nothing there until the function acts on the numbers, and the answer, the outcome, the conclusion must always be a finite sequence. So here's an analogy. It would be a deck of cards where the back of each card has some numeric value. So it doesn't matter what the numeric value is. It doesn't matter, so I haven't put that on the back of this card. And the face has a letter, which is either A, B, or C. And this absurd game has very simple rules, and the rules are, starting from the top of the deck, if the card is A or P or C, when you turn it over, discard it. Discard it, whatever it is, A or B or C, discard it. And ignore the number on the back. Continue until you have removed all the cards from the deck, except for the last one. And I think what I haven't done adequately is talk about the computational aspects of this, despite the subject of the presentation. But I said there would be a bonus slide, and that's about looping, and I'm going to show you that next, and that will be the last slide. Here is an example of a looping sequence, and I used 3x plus 5 as the function instead of 3x plus 1. So the only difference is the addend, and it serves as a counterexample because the only loop in 3x plus 1 is 1, 4, 2, 1. And if you don't look at the even numbers, it's basically just 1 to 1. Nothing's happening, in other words. So, but for when the addend is increased, and this is a great example, 3x plus 5, you get a counterexample. It's a counterexample to 3x plus 1. And it shows loops that just after it starts just fine, it gets into this loop. Why does it get into this loop? Because a number repeats itself. And in this case, it's 49. So there's only really one loop there, and all the others can be ignored. They're just an artifact of the algorithm and the graphing. And if we look on the right, we see that all the numbers in the loop, 49, 152, 76, 38, 19, 62, 31, 98, 49. And then we look at the common differences by subtracting the numbers on the left. So 49 minus 152 is minus 103. 152 minus 76 is 76, and so on. And when you do that and add those minuses and pluses, negative and positive numbers, when you add those up, you get a zero, a sum of zero, and that's why it's a loop. It wouldn't even matter what order those numbers were in. It's just that common differences will always be the same no matter how you calculate them, and they'll always be zero. That can't happen with 3x plus 1. And the reason it can't happen is because there's no inverse possible, no inverse operation possible. That's my latest and best explanation. So when you add an addend greater than 1, you are effectively creating some inverse operations. And that's what produces looping. Well, that's my theory. So you decide which is a harder challenge, infinite sequences or looping sequences. And I thank you very much. See you later. Bye.